The second set is the extra information which is known to has taken place. So this is the probability for B to happen given that A has happened. And it's calculated using the following formula. You take the intersection of the two sets and you divide by the probability of the second set. And as I remarked on the last lecture, the probability for A to happen given that A has happened must be 1. And indeed, you find if you substitute B equals A into that formula, you find A intersection A, which is A. So we have P of A divided by P of A, and that's equal to 1. And that tells you, like, why is that factor present there, right? It's present there to normalize the updated probabilities correctly. So let me now do a few examples illustrating how to use that formula. So in my first example, a fair coin is tossed 3 times. What is the probability that the first toss was tails, given that at least one heads has occurred? Okay, so a fair coin is tossed or flipped 3 times. What is probability that the first toss was tails, given that at least one heads has occurred. So fair coin means that we will be using the equiprobable model, and the sample space contains 2 times 2 times 2, 8 points. So H, 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 T, H, 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 T, T, H, T, H, T, H, T, T, and T, T, T. And the probability for each point is 1/8. Right, that's the equiprobable model. For tossing 3 times. So what is the probability that the first toss was tails? So that immediately gives us one event. Let's call it B. So first toss was tails. So we can find all the points now explicitly. So first we have tails, and then we can have tails, tails, or tails, heads, tails, or tails, tails, heads, or tails, heads, heads. Right, so that's this event. And also another event which we know that has occurred is that at least one heads has occurred. So let's call this A. At least one heads has occurred. And then again, we can find explicitly all the points with at least one head. So H, 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 3 heads. H, T, H, T, H, H, and H, H, T. With 2 heads. T, T, H, T, H, T. NHTT with 1 heads. So we only have to drop one point, t, with no heads at all from the sample space to obtain this event. And okay, so these two events are specified in the conditional of the problem. And let's understand what are we to find. So we're to find the probability of the first event, which we call B, given that the second event, which we call A, has happened. Right? So we're to find this, and we're going to use this general formula, probability of the intersection divided by probability of A. So we have listed explicitly the sets A and B, so we can find the intersection just by finding the common elements. So first toss was tails, and then at least one has occurred. So we've got an intersection THT, TTH, and THH. Right, and so now we can finally calculate this probability. Okay, I'll go back to this formula, I already wrote it. So it suffices just now to calculate the numerator. So I have 3 points in the intersection, so the corresponding probability is 3/8. And in the set A, we have 7 points, and therefore the corresponding probability is 7/8. And this ratio simplifies to 3 out of 7. Yes, please. Well, I don't see any problem. Is this just the probability of that B given A?
Yeah, so
the probability that the first.
Given that the first toss was tails, given that at least one hit has occurred.
Yeah. That's what it says in the condition of the problem.
Right, okay, thanks.
Sure, no problem. Okay. It doesn't matter how you know them, A or B, but just have to stay consistent. Sure. It's important to check. Any other questions with this example? Right? Just some people can do it in their minds. They kind of can get this 3 out of 7 just thinking about the situation differently, but it's not always easy, right? But this formula works always, right? So you can, using it, you can arrive to the correct answer for the conditional probability. Okay, let me do another example. An urn contains 4 red balls and 7 blue balls. Four balls are drawn one at a time without replacement. That's our random experiment. 4 balls are drawn out, one at a time without replacement. Find the following. Part A, what is the probability that the first ball was red? What is the probability that first ball drawn is red? And part B, how is this answer modified if you know that the last 3 balls are red? How is the answer to A modified if you know that the last 3 Okay, so let's do first part A. So to specify the sample space, we can think that our balls are labeled. For example, the red ones can be red 1, red 2, red 3, red 4, and the blue ones are blue 1, blue 2, and so on up to blue 7. So we can label them like that. And then our sample space contains all strings with all possible strings with 4 non-repeating labels. For example, it contains red 1, blue 2, blue 3, red 3, right? So this sequence means that the first ball which was drawn from the urn is red ball 1, the second one was blue ball 2, then blue ball 3, and red ball 3. Okay, so that's our sample space. And we can calculate the total number of elements in it. So here we have ordered selections of 4 objects without repetitions. These are precisely permutations, right? We know that, so we're taking them out of a total of 11 balls, so it's 11 factorial divided by 11 minus 4 factorial, or 11 times 10 times 9 times 8, which gives you 7,920 different configurations. And we will assume that we have an equiprobable probability distribution on this sample space. Right, because we're not given any information which would distinguish any particular sequence of this of the balls. Okay, so we use the equiprobable model on S. Right, so let's next okay, so this was setting up the stage, right? What's our model? Let's address directly now question in part A. So the event which we're interested in is that the first ball is red. So that let this be the event A. The first ball is red. We can count the number of elements in A. So that gives us, so the first symbol must be R1, R2, R3, or R4. So that gives us 4 choices for the first symbol in the string. And then we're not told anything about the subsequent balls. So we start with 11 balls. Once we've drawn the first one, we have 10 of them left, and the second one can be any one of those 10, either blue or red. And then after we've drawn 2 of them, we have 9 of them left. And then in the third position, in the third draw, you can end up with any one of those 9. And finally, you have 8 choices for the last one. Okay, so that gives us the probability of A in the equiprobable model. So it's the number of elements in A divided by the total number of elements. That gives us 11 times 10 times 9 times 8 divided by 4 times 10 times 9 times. Okay, go on. The other way around. Yeah, I thought, oh, it's odd, it looks larger than 1. Something is wrong here, thank you. Sorry, the other way around. 4 here and 11 there. So that we end up with 4 out of 11, which is definitely less than 1. So whenever you calculate and you get a probability larger than 1, that definitely means you made a mistake somewhere. Be aware of that simple rule. So 4 out of 11. This can be obtained quicker. Sorry. Yeah, you can just ignore, say, the subsequent drawings, right? And just think about the very first one. I think that you have to draw 1 out of 4 red ones amongst the 11 balls altogether available. That's true. So you can do this one quicker. I was really like setting the stage for the next question. And see, if you sort of try to use the same logic about the next question, that doesn't make much sense. Because you think, or, you know, why should it matter which balls are drawn in the second, third, and the fourth draw, right? So I'm only concerned with the question whether the first one is red or not. Why should it be modified? So the way to address it properly is to think about the entire sample space, not just the first draw separately, but about the entire experiment with four draws. Right. So part B. Right. Let's introduce the event B, which says that the last 3 balls are red. The last 3 balls are red. So now we can formulate what exactly is that we're after. We're after the probability for A to happen, for the first ball to be red, given that the last 3 balls are red. Right, so that's given, that is known what has happened. And we're going to use our general formula, so that's P of the intersection, and divide by P of B. Okay? So we divide always by the probability of the second one. So we need to calculate the numerator and the denominator. So how many elements we've got in the intersection? So the intersection means that the first ball is red and the last 3 balls are red. So that means all 4 balls are red. And how many elements we've got there? So we have to have, it's going to be 4 factorial, right? So you have your 4 red balls, R1, R2, R3, R4, and the only difference is how you arrange these balls. So that's 4 factorial, which is 24. Right? And therefore, yeah, we can calculate the probability of the intersection. That's 24 over 7,920. Okay? So what about B? B is a set in which the last 3 balls are red. So we have to count the number of elements. So here it doesn't say anything about the first ball, so it can be either red or blue. So let's count separately the situations when the first ball is red. So when the first ball is red, then we have 4 choices for the first ball, right? And then the 3 subsequent balls are also red. 3 choices for the second, 2 for the third, and 1 for the last one, so it's 4 factorial again. But also it may happen that the first ball is blue. So when the first ball is blue, then we have 7 choices for the first ball, and the last 3 balls must be red. Then we'll have 4 choices for the second one, 3 for the third one, and 2 for the fourth one. And therefore the number of elements in B is the sum. So we counted separately configurations where the first ball is red and the first ball is blue. So by the sum rule, we have to sum up these two numbers, and it gives me 24 plus 24 times 7, which is 192. Okay, so finally, we can now calculate the desired conditional probability. So P of the intersection, so that's 24 over 7,920, and P of B, that's 192 divided by 7,920, and you can cancel these denominators and get 24 divided by 192, which, let's see, this can be simplified. So it's 4 times 3 times 2, and here it's 8 times 4 times 3 times 2, so that's 1/8. Okay, so that's the probability in part B that the first ball was red, given that the last 3 balls are red. There might be also a quicker way to get this, but this formula works for any such situation. Questions, please? Let me now introduce independent events. So events A and B are called independent if P, the conditional probability for A to happen given that B has happened, hasn't changed. It's still P of A in the original model. Okay, so it's one way to define this. And it looks like, well, it's a little bit asymmetric, right? When we talk about A and B being independent, we think that they're mutually independent. Right, so A is independent of B and B is independent of A. Well, here on the left-hand side, we chose to have the conditional probability in which A and B are not on equal footing. But actually, using the definition of the conditional probability, we can. I'm going to show now that if this is true, then you can also interchange A and B in the formula. And obtain that the probability for B to happen given that A has happened is also independent, is the same as the unconditional probability. So how do we do that? So if that boxed formula holds, then by definition it means that P of the intersection divided by P of B is equal to P of A. So I can multiply both sides by P of B. Get that P of A intersection B is P of A times P of B. So, and clearly, you know, the two boxed formulas are equivalent. If the first one holds, then I've just shown that the second one holds. Alternatively, if the second one holds, then the first one must hold. I can just divide by P of B both sides, and then again use the definition of P A given B. Moreover, now if I, instead of dividing by P of B both sides, I divide by P of A, dividing both sides by P of A, we get P of A intersection B divided by P of A equals, well, P of A will cancel out, so this equals to P of B, which means that P of B given A is equal to P of B, right? So, you know, this simple manipulation, dividing both sides, relates these three boxed formulas. So, in fact, any one of these three boxed formulas can be used to check that the two events A and B are independent. So all these formulas are equivalent, and any one of them can be used to check the independence. So the three boxed formulae are equivalent. Any one of them can be used to check that two given events are independent. Well, I also want to draw your attention to the middle formula, which has P of the intersection. I've observed often that students, when they calculate probabilities, they make this mistake. They apply this formula to any pair of events A, B. But basically, this is the definition of independence. So you have to be sure that the events A and B are independent to be able to use this formula, right? So just make yourself note that this is true only for independent events. Right? So it's not always true that the probability of both things to happen is the product of those probabilities, or the probabilities of the individual events. Let me illustrate this notion of independent events on the following example. A box contains 10 items of type 1. 3 of which are defective. It also contains 20 objects of type 2 6 of which are defective. Suppose we draw one item at random. So one object is drawn at random. So let A be the event that this object is type 1. and let B be the event that this object is defective. The event that this object defective. Fine. Okay, I want to move over. So find the following: P of A, P of B, P of the intersection, conditional probability PAB, conditional probability PBA, and determine whether the two events A and B are independent. Determine whether A and B are independent. Okay, so let's start calculating. So the event A is that the object is of type 1. So altogether we have 30 objects in our box, and we've got 10 objects of type 1. They're drawn at random, so the probability to draw one of those 10 objects out of 30 is 10 over 30, or 1/3. What about P of B? So the B says the object is defective, so it might be type 1 or it might be type 2. So we just have to count how many defective of both types we've got. We have 3 defective of type 1 and 6 defective of type 2. So 3 plus 6 is the total number of defective objects. So the probability to draw one of them is 3 plus 6 over 30. That's 9 over 30, or 3 out of 10. What about the intersection? Well, it must be 1 and defective, and we're told there are 3 of such objects. So it's 3 out of 30, and the probability therefore is 1/10. Let's calculate the conditional probabilities. That's just, substituting into the relevant formula. So P of the intersection divided by P of B. So it's 1/10 divided by 3/10, or 1 out of 3. And if we swap them, just have to replace the denominator by P of A. So it's 1/10 in the numerator, and P of A is 1/3. So this is 3 out of 10. And now it remains to answer the final question: determine whether A and B are independent. So any one of those 3 boxed formulas can be used, and we've calculated all the quantities which feature in those 3 formulae. So for example, I can take this conditional probability and compare this to the unconditional probability P of A. And I find that they are the same, 1/3. So since P A given B equals P of A, and both equal to 1/3, these 2 events are in fact independent. A and B are independent. Yes, please. Which sentence we should remove? So we say
Now the bottom.
the bottom.
Then that not specific type like that. Let A be the, then that object is type 1. Let's just forget about that.
Well, that's the same thing, right? A is type 1.
Yeah, I mean like this. Assume it's not there. I'm just asking like what type.
Or let's assume it's not there. So you want to remove A. Let's not talk about A at all.
Yeah, and no, let's forget about A. And then probably go to B.
Yeah?
It would change, right?
No? There are, altogether there are 9 defective objects. So we consider these properties to be separate properties. Each object is either defective or normal, and each object is either type 1 or type 2, whatever these things are.
It won't be like you can be defective at type 1 or you can be.
Well, you just disregard. I mean, when you calculate P of B, right, it's just the property of being defective, and you just don't look at it to be type 1 or type 2. You can disregard it, sure, if you don't look at it. So the answer is the same. Yeah, I mean, then if you want to erase all mention of type 1 or type 2, then the formula should, for the problem should be reformulated. It should say the box contains 30 items, 9 out of which are defective. No mention of type 1 or type 2 property. Okay, sure. Anything else?
If A is independent, is B necessarily independent as well?
Yeah. Yeah, that's what I was demonstrating in this. All these 3 box formulae are equivalent. So this says that, well, A is independent of B, you can read it like that, but that implies that B is independent of A. So they're completely on equal footing. Yeah. Yeah, so the answer is yes. Anything else about independence? Okay, you can always ask later. Let's move on. The next thing we'll discuss is random variables. I'll start with the definition. The definition is really simple. A random variable is any real valued function on the sample space. A random variable is any real valued function on the sample space. So we assume some probability model, sample space, and probability function are given. Then any function, call it x, from the sample space with values being real numbers. So that's how we write this with the domain and the codomain. Is called a random variable. Here is a concrete example. So let us consider a fair coin flipped 3 times. Right, this was our example we previously considered. And let S be an element of the sample space, 1 point there. Define a random variable x by the rule x of s must equal the number of heads in the sequence S. The number of heads in S. So that number will be a real number. It will be an integer, but it's a particular case of a real number. So that will be, that will satisfy our requirement on the values. And for example, I'll just write this down here. For example, x of heads, tails, tails is equal to 1. Right, because the sequence HTT, which represents a point in the sample space for this random experiment, contains one H, so one head. So the value is 1. And we can see more generally that there are only 4 possible values. So we can have either 0 heads, which will hold for TTT sequence, or precisely 1, precisely 2, or 3. So 4 different values. So I write this by saying x belongs to this set of values, right? Just for brevity. Another example. Let's look at tossing 2 dice. Again, 2 fair, unbiased dice. The sample space contains pairs of integers, which correspond to the scores on the first die and on the second one. So there's the integers I and j, both between 1 and 6. And let x of ij be equal to I plus j, that is simply the total score. I plus j, that is actually the total score. So this defines, again, a random variable, right? For each outcome, you just sum up the 2 scores, and you get the total score. That's a number. It's a single number. So that's a random variable. And we also can note that all the possible values are 2, 3, 4, all the integers up to the maximum 12. You cannot get less than 2, because the smallest you can get is 1, 1. So the smallest score is 2. And the largest one corresponds to having 6, 6. That's 12. Right, so these are a couple of simple examples of random variables. So next thing I'd like to discuss is that for any random variable, one can assign probabilities to its possible values. So we can assign probabilities to the values of the values of a random general statement, a random variable, by the following rule. I'll first write it as a simple formula, but then I'll draw a picture and we'll illustrate the meaning of that formula. So the probability for the random variable capital X to obtain the value small x is a number, which is one particular value, equals the probability of the set, which consists of points in the sample space S, such that x of S is equal to the value, to the given value. So what does it mean in simpler words? So imagine that this is my sample space, right? So the probability, the random variable x is a function which assigns a value to each point in the sample space. So we can slice up the entire sample space according to these values. So I'll just draw a nicer picture. Suppose I slice it into wedges as a pizza, and I suppose that here, say, x is equal to 0, here x is equal to 1, on that slice, x equals to 10, is another slice, x equals 25, and so on. Right? So this can be partitioned, the whole sample space can be partitioned according to the values of the random variable. And then to calculate the probability for the value, I just take the corresponding wedge, the corresponding subset, and calculate its probability. So we assume that the whole model is specified, the probability function is given, so I calculate the probability of the corresponding subset, and that gives me the probability of the value assigned to the value. Okay. So let me illustrate this on a concrete example. So, for instance, the example I looked at here, define a fair coin is flipped 3 times. Define a random variable x by the rule that it counts the number of heads. Right? These are the possible values. We would like now to calculate the probability for each one of them. So for brevity, I will use the notation f of x, right, for the probabilities of the corresponding values. So how do we calculate? So f of 0, that should be the probability for the set on which we have 0 heads. So there's only one such point, it's TTT, so this is the 1-point subset, and its probability is 1/8. If we have 1 heads, right, that's the second value in the list, so its probability should be the probability of the subset on which we have 1 head. So that's H, TT, THT, and TTH, right? There are 3 points on which the value is 1, and in this equiprobable model, the corresponding probability is 3/8. F of 2 corresponds to the value 2, which for this random variable means 2 heads. So we form a subset into which we include all points with 2 heads. It's THH, HTH, HHT. Again, there are 3 of them, so the probability is 3/8. And the final value is 3, and there's only 1 point for which the number of heads is 3. So this is HHH, and therefore the probability is 1/8. Right? So these are the probabilities calculated for the values. There are only 4 possible values, and these are the probabilities. One simple check is that they still do have to add up to 1. Right? The probabilities for the values have to add up to 1, which we can check that 1/8 plus 3/8 plus 3/8 plus 1/8 is equal to 8/8, which is 1. So that is satisfying. Okay, it's good to have this in mind as a simple check once you assign these probabilities. All right, so that's all for today. We'll have more on this on Friday.